Oh great, my controller just died. Now I have to go get new batteries.
I feel like you just changed those not too long ago.
I did. I'll be right back, guys. I'm gonna run and see if I can find some more batteries.
I wonder how we could get the controller to last longer.
Well, we could just use more batteries, right?
Sure, if we use 2 batteries rather than 1, we should get twice as much energy.
But do you think it matters how they are connected?
I don't know, it might. I can only think of 2 different ways to connect them, in series or in parallel.
I'm not so sure it would be different. Let's test it.
Hey guys, I found a bunch of batteries.
Great, but before you put them in the controller, we thought we'd run a little test.
Oh yeah? Rather than running your test on my controller, can we test it on something a little less expensive? Like a fan, a light bulb, or a resistor?
Why don't we use a fan with a 9 volt? It'll be a breeze.
I'm not so sure. Won't there be some back EMF?
Oh, I guess you're right. What about throwing a bunch of light bulbs in parallel with a 9 volt? That way it shouldn't take too long.
Don't 9-volt batteries have really high internal resistance? Won't that affect our results? You got any other bright ideas?
Fine. What about using AAAs instead of a 9 volt?
That's a good idea, and instead of light bulbs, we can use a resistor.
Sounds like a great idea, guys. It's a good thing we planned this out, or else we could have wasted a lot of time. For our experiment, we set up 3 different circuits. In the first circuit, we used a single AAA battery. In the second, we used 2 AAA batteries in series, and in the third, we used 2 AAA batteries in parallel. To measure the current running through each circuit, we put an ammeter in series with the resistor. In order to measure the potential difference, commonly known as the voltage, a voltmeter was connected in parallel across each battery set. Continuous current and voltage data was collected until the voltage reading was 15% of the original battery voltage. The AAA batteries we used in our circuits each have a voltage of 1.5 volts. In our single battery circuit, the voltage is just 1.5 volts. In our series battery circuit, the voltage is 3 volts. And in our parallel battery circuit, the voltage is 1.5 volts. We used a 17 ohm resistor in each circuit. We predicted that the series circuit would result in twice as much charge moved as the single battery circuit, since there are 2 batteries instead of 1, but would have the same longevity since it has twice the voltage, which would result in twice the current. For the parallel circuit, we predicted that there would also be twice as much charge moved, again since there are 2 batteries instead of 1. However, we thought that this circuit would result in twice the longevity, since the voltage is still 1.5. We graphed the current versus time and calculated the area, which has dimensions of charge in units of amp hours. In our calculations, the charge in amp hours represents the amount of charge moved through the circuit by the batteries. From our experiment, we calculated the amount of charge moved through each circuit in amp hours. We found that we were able to extract 0.5 amp hours from a single AAA battery, 0.5 amp hours from 2 AAA batteries connected in series, and 1 amp hour from 2 AAA batteries connected in parallel. The single AAA battery took 11.5 hours to discharge down to 15% of the original voltage. The 2 AAA batteries in series discharged to 15% in 6.1 hours, and the 2 AAA batteries in parallel discharged to 15% in 19.6 hours. We also graphed voltage versus the amount of charge moved in amp hours. An ideal battery under intermittent usage would maintain a constant voltage for the duration of the usage. The parallel batteries exhibited the most ideal behavior since they maintained a stable voltage for a long period of time. Our single battery also behaved fairly ideally. However, the series batteries did not maintain a stable voltage for any significant amount of the duration. So I think we're out of batteries again.